In the name of God, welcome back to this series of lectures or tutorials on kinetic theory of gases. So far we've already got like 3 lectures. The first one was an introduction. The second was a recap on probability, what it means and what we can do with it concerning this theory. Number 3, we delved into this topic of probability densities and related integrations, the Gaussian integration formula, and some other formulas that can be derived from that. In today's lecture, which is going to be the 4th one in this series, I'm going to talk about statistical definition of temperature. So usually the system we take into consideration for discussions and for these lectures is a system of gas. In place of that, one can think about any other thermal system, and for such systems we usually can think about or address 2 important properties. One is kind of, so to say, a global property. So global properties, or maybe better word is the macroscopic features or characteristics of the system, of the thermal system under consideration on one hand, and on another hand there is this let's say tiny or kind of microscopic properties. So there are microscopic properties. So if we take a gas, an ideal gas, as an example, one can talk of let's say temperature. So temperature is a macroscopic feature. The same thing with, let's say, energy of the system, and there are more examples which hopefully we're going to talk about over this set of lectures. Microscopic properties are kind of let's say the opposite of macroscopic or global properties. So they are kind of things arising from atomic, let's say, so atomic properties, as opposed to these global properties, or a combination of atomic properties actually give birth to the let's say macroscopic features. An example is, let's talk of spin, for example. I can talk of spin of a gas, let's say, right? So this is a macroscopic feature. Okay. Usually we don't say measure microscopic properties of thermal systems in the laboratory. So meaning that if I have a gas as a sample, one wouldn't like pick one of the molecules of that gas and then follow it to see or to measure what microscopic properties it may have. Right? But on the other hand, macroscopic features are things we deal with. They're, so to say, measurable in the laboratory. So one can measure the temperature of a system of gas, the energy, and so on and so forth. Yeah. So the take is that usually these atomic or microscopic properties, when combined in a system with many atoms or with many molecules, this usually gives birth to the macroscopic features. So it may be some sort of in a complex manner. So the individual macroscopic properties of the atoms integrate into macroscopic feature of the system. So it may not be a linear transformation. It may be an emergent kind of phenomenon. But the message is that, for example, if one consider temperature, one can think about the temperature being coming from the microscopic properties of the system under consideration. Okay. For illustration, to start very simple, so let me write as an illustration. One can consider, let's say, a bag or a box with, let's say, 100 coins in it. So a coin has this feature that if we take a coin inside a box, from inside a box containing many coins, the outcome of the coin we pick and look randomly, the outcome is going to be one of these two. Either we see a head of the coin, or we see the tail of the coin. So maybe we can label head to be H and the tail to be T. Zeros and ones are also used, but here let's stick to that. So we consider a box or a bag with 100 coins inside it. And supposing that we pick coins one at a turn and then look to see what comes out. Okay. As an example, I can write something like this to say that looking at the first coin number 1, the outcome turns out to be a head. Coin number 2, this is just an example I'm cooking up of head, turns out to be a head also. Let's say coin number 3 turns out to be a tail, and so on. We keep looking until we finish the number of coins inside the box. So coin number 100, let's assume, let's say it turns out to be a head. Okay, this experiment, the outcome of this experiment can be simplified into something like this. So maybe I arrange the outcomes in this way. I have first a head, and then a head, and then a tail, and then so on and so forth. And the last one, the 100th one, is turns out to be a head. Okay. If I write it, the outcome in this manner, okay, one can consider this the series of outcomes to be like a particular state, a particular possible state of the system we are considering. The system we are considering is a box containing 100 coins. Okay, so this is microstate of the system. Okay. We have information about the outcome of the individual tries of taking a coin out of the box and then looking to see whether it is a head or a tail. Yeah. So this is one example. Another example is that, for example, we can have a scenario. Let's say we have a scenario where, okay, this is a thought experiment where the outcomes, let's say all of the outcomes, number one, coin number one is head, coin number two is head, coin number three is head, all of them up to coin number 100 turns out to be head. This is another possibility, right, of the state of the system. Another possibility is that we have outcomes as tails instead. So all of them are tails. This is another independent microstate of the system. Another example is we can have, let's say, the first 50 to be tails while the last 50 to be heads. Okay, this is also an independent microstate. Besides this, one can put a summary. For example, from this particular microstate, I can write that we have, let's say, okay, we have 100 heads and 0 tail. Okay. For the next one, I can write that we have as outcome 0 head and 100 tails. Okay. For the next one, I can write that we have 50 heads and 50 tails. Okay. Right. So the left-hand side, we're talking about microstates of the system, right? And I can summarize these microstates in this way. Yeah? A generic macrostate, on the other hand, is that, let me write an example here. So we have macro state of the system. Macro state of the system, right? I can write a macro state in this way. So I have 50 heads and 50 tails. Okay. Here, when we talk about macrostates, let me draw a line to differentiate between the two. We have the summary that is the outcome of the experiment is that we have 50 heads and 50 tails. But there are so many ways of getting this. Okay? One way is, for example, would be this particular microstate. What does that mean? It means the first coin is a tail, the second coin is a tail, the third coin is a tail, that way up to the 50th coin. Okay? From 51 to 100, each and every one of those, the coin turns out to be a head. Okay? So this is a detail, this is an atomic feature. I know I have information about each one of the coin taken under consideration. It could also be that the first coin is a tail, right? The second coin turns out to be a head, the third one a tail, the fourth one a head, and that way alternating. The 99th one is going to be, let's say, a head, and let's say a tail instead, and the 100th one is a head. So alternating, one is a tail, the next one is a head, and the next is a tail, and the next one is a head, right? So this is a different arrangement. This is a different microstate. This is a different microstate compared to the previous one. So the previous one is that, right? But for both of them, this and this, the macroscopic feature is that we have 50 head and 50 tails. So I hope you can see that for macrostate, we're not concerned about the atomic property or the individual outcome of each and every coin. Okay, that would be a microscopic feature if we care to bother and if we really want to know the first, the second, up to the 100th coin, what the outcome is. Okay. So for a given macrostate, I hope one can see that there can be several, there can be many different microstates that could lead to a single macrostate. Okay. So I have given an example here, the macrostate with 50 head and 50 tail can be obtained from this microstate and also from this microstate. Right, and there are many ways one can do that. Another example, let's say a macrostate has 33 heads and 67 tails. Okay. This is a macrostate. There are many ways of getting this macrostate from different possible microstates of the system. So this is a combinatorial problem, and I'm going to show the formula for that. Okay. But before going to that, let's take a deeper look with another example to have hopefully a clearer picture about what I'm talking about concerning macrostates, and microstates. So let me write something here to summarize what I've said. Same microstates macrostates can be obtained via many different microstates. Okay, to make a simpler example, consider a box with 3 coins inside it. Right. If we make an experiment of drawing out, picking these coins one in a turn, and the possible outcomes are, for example, we may have a head and a head and a head. So that is 3 head, 0 tail. We may have a head and a head and a tail, right? A head, a tail, and a head, a tail, a head, and a head, a head, and a tail, and a tail, a tail, a head, and a tail, 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 head, tail, tail, tail. So this is 2 head, 1 tail. Okay, this is 2 head, 1 tail. This is also 2 head, 1 tail. This is 1 head, 2 tail. This is 1 head, 2 tail. This is 1 head, 2 tail. The last one is 0 head, 3 tail. Okay. So hope this is visible. You can see, for example, these 3 examples. Okay. That 3 different microstates leads to the 2H 1T macrostate. So I hope you can see that. If we consider 2H 1T to be a macrostate, that is without worrying in detail about which of the coins turns out head or tail, then that is a macroscopic feature. Okay? So we can see that this macrostate can be obtained actually from 3 different microstates. So this is microstate number 1, this is microstate number 2, this is microstate number 3. You see that for microstates, the details of where we're having heads or tails really matters. So the first microstate, the first coin is a head, the second coin is also a head, the third coin is a tail, right? And for the second microstate, the first is a head, the second is a tail, the third is a head. The third microstate, the first coin is a tail, the second coin is a head, the third coin is a head. So for microstates, we really worry about details of the individual atoms. Here, the atoms we consider to be coins. The detailed property, features of the coin is important when talking about microstates. On the other hand, when we're talking about macrostates, we're not really concerned about the details of the atoms. We are not really concerned about the coins in this example, which of the coin turns out to be a head and which one turns out to be a tail. This is not important. And you can also see this in the second example. Here, let me take a blue color. So again, this is 3 different microstates. 3 different microstates leading to this macrostate with 1 head and 2 tails. So this is an example of macrostate. Which can stem from 3 different microstates. So the 3 different microstates are here on the left, which you can see. Okay. If I cycle this 3 head, 0 tail, and also this one, 0 head, 3 tails, one can consider macrostate with 3 heads and 0 tail. You can see that there is only one possibility of a microstate. So all the 3 coins turn out to be heads. Or this one, there's only one possibility. All the coins turns out to be a tail, right? But I hope it can be seen also that for this system, for this example of a box containing 3 coins, the total number of possible microstates, number of possible macrostates, total number of possible macrostates is 2 to the 3. In this case, it's going to be 8. So I can talk about probability in the sense that, for example, being a frequentist, I can do this, say, probability of a macro state having 3 heads and 0 tail. If I write the probability in this way, this is going to be 1 out of 8, right? And I can talk about the probability for the macrostate, let's say 2H1T, right? So for the macrostate 2H1T, there are 3 different microstates that can lead to that. So the probability is going to be 3 divided by 8. I hope we begin to see a connection between the number of possible microstates, right, and the macroscopic feature of the system. The thing is that I can take a system under consideration. Here, my system again is a box with 3 coins. One macroscopic feature, one macroscopic property of this system is written this way. I have 2 heads, 1 tail, right? And it is an interesting question to ask, what is the probability of the system being in this macroscopic state, right? You can see that I can compute the probability using simple statistics, knowing the total number of possible ways of arranging the coins inside the box, and knowing the total number of microstates which can lead to the macro state under consideration, then I can compute the probability. Okay? So in this way, this is a very simple example to begin with for setting the terminology of this part of the lectures. Our aim is that we would like to connect temperature. So temperature, if we define it as a macroscopic feature, macroscopic property of a system, we're going to connect temperature with statistics. In some other way, we say there is a link between temperature, which is a macroscopic property of a thermal system. There is a connection between temperature and statistics. So statistics, that is, we are talking about probability. We are talking about the number of different possible microscopic states that can lead to a particular macroscopic number, which we call temperature. Okay, so this is actually the aim of this lecture, statistical definition of temperature. So we can see temperature is a macroscopic property. It can be linked to statistics. It can be linked to probability. Okay, so let me go to the next page. And write this for gases and other thermal systems. Temperature represents temperature is a macroscopic property of the system. So the values temperature take the values, the magnitude it takes can be linked to some microscopic properties of the same system. In this way, we connect temperature to statistics or probabilities. Just like the example I've given before. Okay, so to take another step forward, let's go back to the 100 coins example. 100 coins in a box. Okay. For this example, number one, the total number of possible configurations. So configurations mean arrangements or the outcomes of the experiments where we take a single coin at a time until all the coins are out of the box, and then we look at the outcomes of how many heads and how many tails we have. Okay. So the total number of configurations, possibilities of microstate possibilities is equal to 2 to the power 100, and this is approximately 10 to the 30, so this is a huge number. Okay. And aside here to see how you can get this conversion, so we want to write 2 to the power 100 in a form 10 to the something, so let that be x, 10 to the x. We want to find x. X is approximately 30, as I've written above. Taking the logarithm of both sides, so implies that log of 2 to 100 would be log of 10 to x. So log here is like log to base 10. And what happens here is that we have 100 times log to base 10 of 2 is going to be equal to x. And if you do the arithmetics, do the multiplication, this is going to be approximately equal to 30. X is equal to 30. Note number 2, if the system's microstates are uniformly distributed, so if these configurations are equally likely, equally possible, each one of them, sorry. If the configurations, or each and every one of these 10 to the 30 microstates are equally likely, that is, the probability of getting one is same as the probability of getting the other, then the probability of each microstate is going to be approximately 10 to the minus 30. So it's really, really tiny, right? Look at this. We're talking about microstates. Probability of a microstate. On the other hand, I can talk about probabilities for the macrostates. So, probability of macrostates of the system will depend on the number of microstates that could lead to the chosen macrostate, right? So this is not straightforward. You have to count the number of possible microstates that could lead to a single macrostate, and then from there you will be able to compute the probability for the macrostates. So just like the example we've looked at in the previous page. Okay, so let me go to the next page. Let's say we have a macrostate written in this way for macrostate, which is written in this way. So R number of heads and N minus R number of tails. Where here what I have written for the example we're looking at of 100 coins inside a box, N is going to be 100. So N is fixed, right? So R is going to be number of heads, and N is going to be total number of coins. So this is a macrostate. And the number of microstates, that could lead to this particular macro state, which I have written above, is, so this is a combinatorial problem. This is equal to NCR, also written in combination R. This is defined this way: N factorial divided by R factorial. Divided by N minus R. So an example is here we can write number of ways to get a microstate with 50 heads and 50 tails. If you write it in this way, the number of ways you can get that is 100 C50, and this is going to be 100 factorial divided by 50 factorial times 100 minus 50 factorial. This is approximately 10 to the 27 possible ways or possible microstates. So out of the 10 to the 30 total number of possibilities, 10 to the 30. Out of this 10 to the 30, 10 to the 27, there are 10 to the 27 possible ways of getting this macrostate, 50 head, 50 tail. And you can compute similar, some other examples in a similar way. So one can write the probability of having the macrostate 50 head, 50 tails is going to be equal to, it's going to be approximately equal to 4 times 10 to the 27, the total number of possible ways of getting that particular macrostate divided by 10 to the 30, which is the total number of possible macrostates of the system. And this is approximately 4 times 10 to the minus 3. So you can see again in this example, we assign a probability to a macrostate, 50 head, 50 tail, right? So in some way, one can talk about the most probable macrostate of a system, right? The most probable macrostate of a system is the one which has the maximal number of microstates that could lead to that macrostate, right? So maybe one can write, summarize in this way, the most probable macrostate is that which is associated with the maximal macrostates that could lead to the macrostate. Yeah. So this is something which is going to be very useful later on when we apply this concept to the case of the macrostate, or to the case of the macroscopic property which we call temperature. Okay. To make the transition, we've already mentioned that temperature is a macroscopic feature of a thermal system. The same thing, another example is energy, which we have also mentioned. So let's now consider a thermal system in a macroscopic state with energy E. So we consider the following. Energy E. So I'm going to write it this way in a box, just like we've been doing before, to indicate that this is a macrostate of a thermal system. So this is representing macrostate of a thermal system. And let's suppose that this macrostate stems from omega. Omega is a function of E. E is the energy, the macroscopic level of the system we're considering. So omega is the number of different microstates. So this is number of distinct microstates leading to the macro state with energy E. Okay. So to make an example, which is a very rough example, I can identify energy with this 50 head, 50 tail macrostate of the example we've considered before. And this can be mapped to, or we can get this particular macrostate from omega, which is a function of E. As we have computed above, omega is going to be approximately 3 times 10 to the 27. Okay, or let's say 10 to the 27 microstates. There are 10 to the 27 different microstates that lead to the macrostate with energy 50 head, 50 tail. This is a very rough example. Okay. But we're considering a thermal system, so we can talk about energy, we can talk about temperature later on. I'm starting with the macroscopic variable energy, and for getting a particular energy E, there are different number of possibilities of microstates of the system, the thermal system. So the thermal system could be a system of ideal gas, okay, and the different possibilities of arrangements of the molecules of this ideal gas, the different microscopic features, the different atomic features of this microgas, of this ideal gas leading to the macroscopic energy E, the total number of microstates, we call it big omega. So capital omega, a function of E. Next, we're going to consider two of such systems, two of such thermal systems. So if I write them like in a box, I have, okay, let me pick a pen. I have a system number 1 with energy E1 and corresponding number of microstates omega, which is a function of E1. Okay, so this is system number 1, thermal system 1. On the other hand, I can consider another system with energy E2 and corresponding number of microstates omega, function of E2. So this is another system. We call it thermal system 2. Okay. If we connect these two systems, so they become thermally connected. What happens? So we're talking about thermal systems. So a thermal system can have energy, it can have temperature, it can have some other properties, I don't know, volume, density, so on and so forth. Connecting these two systems and then isolating the combined system, so the two wouldn't talk to the environment, they just talk to each other in a thermal way. A possibility is that if one of the two systems is hotter than the other one, then we get heat transferred, right? So heat is transferred from one system to the other. By so doing, the energy also changes. So the energy of the two systems will change with time if we connect them thermally. So assuming that these two systems are isolated from the environment, but they are thermally connected, then we can write that for sure E1 plus E2, the total energy of the two systems, if we call this to be capital E, then this is going to be a constant. This is going to be fixed over time as energy, temperature, or temperature is being exchanged, right? So before going further, let us consider another example, which is so we are moving away from the toy examples where we consider coins inside a box into a more physical example. So e.g. consider a system with 10 atoms. This is not 16, 10 atoms. Let's suppose that each atom can exist in a state with 1 unit of energy. So 1, let me write here, or 0 unit of energy. Yeah. And the task we would want to consider is that we want to compute A omega for the case where E is going to be 10 and B omega for the case where E is going to be 4 units. Okay, so here is 10 units of energy. For the case B, we have 4 units of energy. Okay. So we have 10 atoms. Let's say we draw them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For the first case, okay, we have 10 units of energy, so it's like omega is going to be NCr. So here N is 10, so we have 10 places for atoms, and R is 10 atoms with unit energy. So this is going to be like 10 factorial divided by 10 factorial times 0 factorial. Okay. And so this is going to be equal to 1. So there is one way which I can arrange such 10 units of energy over 10 atoms. So each and every atom would have energy equal to 1. So we can maybe paint the atoms to indicate that they have energy 1 unit. Okay. But for case B, if we take this to be B, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms. But let's say only 4 of them have energy equal to 1. So the ones I'm painting have energy 1. So this has energy 1. Unpainted atoms have energy 0 energy. Okay. So how many ways can I arrange these 4 units of energy over 10 possible atoms? Here omega is going to be equal to 10 factorial divided by 4 factorial times 10 minus 4 factorial. Okay. This is going to be like 200. So there are 210 possible ways. So the example here, I'm just trying to again make illustration that for a given energy, here energy 10, the number of possible states, the number of possible, sorry, I'm trying to pick a pointer. The number of possible states, E1, is found to be 1. Okay, the number of microstates. But in the second example, B, where I have 4 units of energy, so 4 ways, 4 things to arrange over 10 possible places, right? So 10 is going to be 10C4. You compute, there are 210 possible ways of doing that. So each and every one of these possible ways of arranging the energy of 4 units of energy over 10 atoms is a microscopic feature. So this is the one I have written here explicitly is an example of one microstate, an example, one possibility of getting energy 4. Okay? So E2, for example, is 210. Here, E1, for example, is 1. So one can consider that the systems are isolated initially, but then we connect them. Probably one is hotter than the other. We're talking about thermal physics. We're talking about temperature. Then we release the system. It evolves with time with the constraint that it doesn't talk with the surrounding. So E1 is going to change, E2 is going to change, but the sum E1 plus E2 is going to remain fixed. As E1 is changing, so omega of E1 is going to change, and as E2 is changing, so also omega of E2 is going to change. Okay. For the combined system, if we think about it, system 1 and 2 combined, the number of possible states, omega function of E, is actually going to be equal to omega 1 function of E1, omega 1, meaning for number of states for system 1 times number of states for system 2, which is going to be a function of E2. Okay? Remember that we have E to be equal to E1 plus E2, which is fixed. For each state of system 1, there's going to be omega 2 possibilities of system 2. Therefore, the number of possibilities, the number of microstates for the combined system is going to be this multiplication. So it's going to be omega 1 times omega 2. So maybe here we put the label, omega 1 here, omega 2. Okay. I go to the next page. And when the two systems are thermally connected, for long enough, then the combined system will eventually reach an equilibrium state. Okay. But after reaching the equilibrium state, then we can talk about the macrostate of the combined state. Okay? And the most probable state, macrostate of the combined system, is the one which is going to maximize omega of E. Right. So if we assume, this is a reasonable assumption to make, assuming that the most probable macrostate of the combined system in equilibrium, after reaching equilibrium, is the one that maximizes omega of E equal to omega of 1 function of E1 times omega of 2 function of E2. This is something reasonable, right? the most probable macrostate is the one that has the most number of microstates. So we can translate this statement into an equation, i.e. we can say d by dE1 of omega E1 omega 2 E2 should be 0 somehow. Okay, so we're differentiating with respect to E1 because E1 plus E2, remember, E1 plus E2 is fixed, is constant over time. So as E1 is changing, E2 is also changing, but both of them change in a way such that E remains fixed. So actually we have one variable, we can take it to be E1. So that's why I'm differentiating omega 1 times omega 2 with respect to E1. Okay. And if you solve this, make the differentiation, so we're going to have, you differentiate d omega 1 dE1 times omega 2 plus, we keep omega 1 and then differentiate omega 2 with respect to E1. This is going to be 0. But also here we can see that dE1 is going to be equal to minus dE2. Okay, because E is fixed, and meaning that we can say dE2 by dE1 is going to be equal to minus 1. Okay, so here keeping omega 1, differentiating like omega 2 with respect to E1. Okay, this can be changed into d omega 1 dE1 omega 2 plus omega 1 d omega 2 by dE2 times dE2 by dE1 is equal to 0, and that is d omega 1 by dE1 omega 2 minus omega 1 d omega 2 by dE2 is going to be 0, and it gives this results. When you rearrange, you can get 1 over omega 1 d omega 1 by dE1 is equal to 1 over omega 2 d omega 2 by dE2. So this is very nice in the sense that I hope we can see that this is an equation where the left hand side represents variables of system number 1, and the right hand side has variables of system number 2. So actually this is saying that at the end of the day, waiting for a long time, after reaching equilibrium, the system reaching the combined system 1 plus system 2 reaching equilibrium, then we have this nice equation. Okay, this nice equation is saying something which is very important. It is saying that there is something which is constant over both systems. Okay, and that constant is actually what we're going to call temperature. Okay, so so the combined system reaching equilibrium has some quantity. This quantity, we write it as d log of omega all over dE to be the same for both system 1 and 2. So see that 1 over omega 1, the omega 1 by dE1 can be written as d log omega 1 over dE1. Okay? So maybe I don't need to write that. It's just absorbing 1 over omega 1 into the differentiation, and then you have that. So this is constant. This is what the equation is saying. We have something which is constant, which is the same for both system 1 and system 2. Okay, go to the next page. So we can then, having some information, having some knowledge that if two systems are thermally connected and allowed to evolve over long enough time, then the system would reach thermal equilibrium. Reaching a thermal equilibrium actually means the system, the combined system 1 and 2, would reach the same temperature. So starting from two different states, we have system 1 independent of system 2. System 1 is going to have its own temperature, its own energy, its own number of states corresponding to the energy. The same for system 2. It's going to have its own energy, its own temperature, its own number of states corresponding to the energy. But when we connect the two systems together, so they're thermally connected, then it's possible that heat will get transferred, let's say, from the hotter system to the cooler system. What happens as temperature is being redistributed? The energy also gets redistributed. The number of possible states also gets redistributed until the combined system 1 and 2, isolated from the surrounding, reaches a thermal equilibrium. At thermal equilibrium, we have found out that something remains constant, and that thing is d log omega 1 dE1 is equal to d log omega 2 dE2. So, which implies that we can define 1 over kb T to be equal to d omega 1, which is equal to d log omega 2 divided by dE2, where T is a constant of the combined systems at thermal equilibrium. So this is a Q. Okay. This is what we call temperature. Yeah. Kb is another constant. It's called Bolzmann's constant. Yeah. And there you go. This is thermal statistical definition of temperature, in the sense that we connecting temperature, which is capital T here, with statistics. So statistics concerning number of possible microstates of the system under consideration. Okay? One may question that why did we choose this particular form for the constant of the system? Why is it 1 divided by Boltzmann constant times temperature? Okay. The reason is that with this definition, one will be able to derive ideal gas equation. Remember, I think from lecture number 1, where we have written the semi-empirical equations, right? Relations of pressure, volume, and temperature for an ideal gas, right? With this choice for the constant, as we're going to see hopefully in the future, one is able to reproduce, one is able to derive the ideal gas equation with this theoretical setting, with this linkage, with this relationship between temperature and statistics, or the number of possible microstates of a thermal system. So I hope this is useful, and you can see that this equation written here is a thermal definition of temperature, which I'm going to write it like 1 divided by kBT is equal to derivative of logarithmic of the number of microstates with respect to energy. So this is very, very nice example. If you have any system and if you're able to compute the number of microstates of the system depending on energy, all you need to do is to differentiate the logarithmic, the natural logarithm of the number of states with respect to energy. And from that differentiation, you're going to get the temperature. Okay, knowing the Boltzmann constant, which is just a number which you can read out and find the temperature. Take care that here actually we are differentiating a function of energy. So you have to be careful depending on the nature of this function. I can have the derivative to be negative or positive. So temperature can be negative. It can also be positive. And also I need to mention here that the unit of temperature is in Kelvin. So T is in Kelvin. So we're talking about absolute temperature. It's an absolute temperature, but you can have some funny or some exotic systems, exotic physical systems which have a number of states depending on energy, kind of behaving in a way where you can have T, the temperature, to be negative. So depending on how you differentiate omega, so it's a property of the system. I think that's it for today. I'm going to say goodbye until next time. Hopefully catch you next. Bye.